Hello again and welcome to my engineering and science channel. Looking back through history, the real workhorse and the driving force behind the Industrial Revolution was a steam engine. The steam engine was initially thought out by guys like Thomas Newcomen and then further developed by people like James Watt, who made them a lot more efficient than they were. Problem is with steam, they're incredibly inefficient, and as you know the laws of thermodynamics, you can't create or destroy energy, you can only change its form. And these engines used to lose loads and loads and loads of energy in the form of heat. So they were grossly inefficient, so we needed something that was a bit more inefficient. As an example of one of these engines, if you look at this from Kevin Coyd Museum, even though it's a fantastic piece of engineering and a really beautiful machine, they're incredibly inefficient and need loads and loads of maintenance. Now, with the advent of the electric motor and research done by people like Nikola Tesla, he's developed a three-phase motor. Now, once again, you can see an example of this three-phase, one of these three-phase motors, once again at Kevin Coyd Museum near Neath in South Wales. But what you can see is a machine that's far more efficient, reliable and simple to run than a steam engine. Now, this particular one was running the fans for ventilation of the mineshaft. Now, with that in mind, what I want to do is talk about the actual winding arrangements of three-phase electric motors. And if we look at this, so as you can see, we have two kinds of winding arrangements here. This is obviously an induction motor. And first of all, the winding is in star. So you've got your three windings, your three phases, which will be your brown, black and grey phases. And as we can see from the drawing, you've got your line voltages across the lines, and then you'll have your phase voltages across the phases. And if you look at the formulas here, you'll see V line is equal to √3 times V phase, and I line is equal to I phase. Now, looking at the delta configuration, it's like a Greek letter delta, like a triangle. And so the phases are now connected differently. And with the delta configuration, we can see that V line is equal to V phase, and that's pretty obvious by the way it's drawn out. And I line, so the current in the line, is equal to √3 I phase. So two different arrangements for the different windings. But if you think about it, our power distribution is distributed in three phase, and if we think of our 415 voltage, our I line, our V line, sorry, so V line will be √3 V phase, and if you have a line voltage of 415 volts, what you'll find out is the times the V phase, the phase voltage will be your 230 volts. So what I want to do now is have a look at an example of how we can do some calculations in this. Okay, so if we look now, we can see we have three resistances connected in star. Each resistance is 50 ohms, so that could represent the resistance of the star windings. And the line voltage is 400 volts. And what we want to do is calculate the phase voltage and the line and phase currents. So if you remember, V line is √3 V phase and I line is I phase. What we can say then is V phase is equal to V line over the √3. It's just rearranging that equation. Okay, so let's just pop some figures in. So V phase is equal to 400, which is V line, over the √3, which is 1.73. So if you do the square root of 3, it's 1.73. And that will give me a phase voltage of 231.2 volts. which you should be familiar with, because 400, if we distribute around about 400, we're going to get 231.2 volts. So next we can say I line is equal to I phase, but to calculate I phase is going to be the voltage 231.2 divided by 50, which is the resistance of one of the phases. So that'll give me an I phase of 4.62, and that's obviously amps. Now, because I line is equal to I phase, we can say the line voltage, I line, is also going to be 4.62 amps, because they're the same as each other. If we change the configuration now from star to delta, using the same winding resistances, and we ask ourselves the same question, finding the phase voltage and the line of phase currents, well, we know now that in delta, V line is V phase. So V line is equal to V phase. So therefore, if V line is equal to 400, then therefore V phase is equal to 400. And obviously they are both volts. Now then, I phase. If we work out the phase voltage, I phase is going to equal the phase voltage over the resistance, which is 50. So it's 400 over 50, which gives me 8 amps. So now what I want to do is work out I line. So I line, so the current in the line is going to be root 3 times I phase. So if we pop those figures in, it's going to be 1.73 times the phase, which is 8, which will give me an I line, or current in the line is going to be 1.73 times 8, which is 13.84 amps. And that's how we calculate the line voltages and phase voltages, and line currents and phase voltages in star delta wound motors. Hope that's been interesting and helpful. Thank you very much. See you next time.